That was poor form on my part. Hello, everybody. Welcome to the February 13 Astro Cafe. And it is my great privilege and honor to invite our first in-person guest speaker since, I guess, February, maybe March 2020.
Samantha was here in September, but yes.
Oh, yes. Okay, but that wasn't a science talk.
No.
This is our first science talk. Okay.
Yes, it is.
So, Sara,
Well, we had someone else too, Randy.
in person?
Oh, in person, not in person.
Yeah. No. It's that we actually had people in the room with our speaker, and I'm really pleased about this. Sara, I'm not going to do much of a biography, but a doctorate in Cambridge, came to Victoria. I'm looking at this. Oh, first of all, went to Chile to the ESO in 2000, and then arrived here 20 years ago, 2003, and has been very productive. What is it? It says 178 co-authored papers, which is just fantastic. And as I look through the list, you are a galaxy person, and galaxies keep getting in the news. It is such an active field of research, and certainly for our astro imagers, it is a favorite subject. And I happy that we have a title tonight, which I don't have in front of me, but it's going to go right back to the beginning of understanding galaxies and then bring us to today. And so with that, a brief history of galaxies. Thank you, Sara. From the discovery of island universes to a clash of the Titans. How wonderful. Please take it away, Sara.
Okay, thank you so much, Randy. That was a very kind introduction. Can everybody on the Zoom hear me okay? Great, I can see thumbs up. So Randy asked if I could give a sort of a repeat performance of a talk that maybe some of you already saw after the Silent Sky production that has just finished its run at Langham Court, that Jim and I had the real privilege to be participating in as science advisors. What I proposed to Randy was that I give a sort of an abbreviated version of that, mostly because I think you folks probably know a lot of what the content was already, but also wanted to have a chance to show you a little bit of my own research as well. So I've sort of blended these two talks together, and we'll see if it works. hopefully it all goes smoothly. So just whilst I've been giving this little preamble, you've been watching this very nice movie, which is a computer simulation of two galaxies merging together. And so what I'm hoping to do with this talk is to give you the brief history of how we came to realize that our Milky Way galaxy was not the only galaxy in the universe, right the way through to this research which looks at what happens when these behemoths interact and how they build up the really giant galaxies that we see around us today. So this is where I always like to start. This is, of course, our view of the Milky Way galaxy as we can see it from a nice dark site. And as you all know, because you're all keen amateur astronomers, is that what we're looking at here is an image through the plane of the Milky Way galaxy. And so let me just get my cursor here. We can see these nice dark dust lanes, but I always like to put this in perspective for folks who aren't used to seeing this image why we get this view. And this also sort of sets the stage for appreciating that we're just one of many galaxies, is that if we were able to step outside of our Milky Way, we think it would look something like this, a beautiful grand design spiral seen here in its face-on orientation. And so it has this bright central nucleus. It's reddish in color, as we know that the center of our own Milky Way is reddish just because it's composed mostly of older stars that have cooler colors, and then more brighter bluer colors in the more active star formation regions in the disk. But of course, if you flip this view 90 degrees, we expect that we would see something like this. And so now we can understand why we see this path of light and dust across the night sky, because of course our place in our Milky Way galaxy is somewhere about here. If you can see my cursor wiggling, about 2/3 of the way out from the center. And so when we look above and below the plane of the disk, the stars that we see in the night sky are just this very thin slab through the disk. But when we look along the plane of the disk, of course, that's where we're seeing most of the stars and most of the dust as well. And so now we can understand from this view of other galaxies why we see what we see from our place on Earth. But now, of course, the contrast is that with the naked eye, this is really the main view of a galaxy that you get. But of course, very deep imaging now has shown us that we live in a universe full of galaxies. And this image was actually up on the screen across from me for the first half of the meeting. So this is, of course, this amazing deep field taken by the James Webb Space Telescope. It continues to blow my mind when I put this in the perspective of how big this image is. So the size of this image is a grain of sand held at arm's length. So it's this tiny, tiny patch of sky that Webb stared at for some 12 hours. And there are thousands of galaxies on here. Just a handful of these sources of stars. So you can tell the stars because they're the ones that have these distinctive diffraction spikes. But everything else on here is a galaxy. So even in this very, very tiny patch of sky, there are thousands of galaxies. And so, of course, extrapolate that over the whole sky and you have a universe full of billions of galaxies. And it's really only been in the last 100 years that we have appreciated the magnitude of this universe of galaxies, because prior to that, there was this big debate about our role in the cosmos. And so that's the brief story that I'm going to tell in the first half of the talk. So our story doesn't actually start with galaxies, it starts with comets. How many folks got to see the green comet that was passing through? Yeah, a few. Yeah, it's always tricky. Some waves on Zoom. So it's always tricky at this time of year trying to actually catch a clear night. But I was traveling, unfortunately. Like, not unfortunately, I was traveling, but it meant that I didn't get to see it. But anyway, this is a beautiful view of a comet. I can't remember which one this is that I got the image of. And then the image of this chap in the top left is Charles Messier. So Charles Messier was a French comet hunter back in the 17th century. And so he was interested in trying to discover new comets. And he basically conducted this search with two parameters in mind. So he knew, first of all, that comets looked very different to stars and planets because they were extended fuzzy objects. And so the comet's main body, its nucleus, is made of different types of ices, and then there's all sorts of dirty, gritty dust in there as well. And so as the comet comes in, plunges towards the sun, the radiation from the sun evaporates material from that dirty snowball and causes the tail, which is always pointing away from the sun because the radiation pressure is pushing away that material from the source of the radiation, i.e. the sun. So Charles Messier knew that these things looked fuzzy because they had these extended coma and these long tails. And the other thing that he knew is that comets move very quickly. And so when he came to observe them night on night, he knew they would be in a different part of the sky, moving slowly, but systematically relative to the fixed patterns of the stars. And so when he was using these sort of two parameters to search for comets, the first thing he was looking for was a fuzzy object, and then he'd come back and re-observe it and see whether it had moved. he found that there were a number of fuzzy objects in the night sky, but they weren't comets. They weren't moving relative to the background stars. So they were nuisance objects. And so he made himself a handy cheat sheet of fuzzy objects that aren't comets, so that he could kind of check these off as he was doing his scans of the night sky. And so it was this list of fuzzy objects that aren't comets that became the Messier catalogue. So there's about 100 objects in the Messier catalogue. This is a mosaic of postage stamps of these objects. And so they're all numbered. So you read across the 10s in the top row. So this is, object 1 through 10, and then 11 through 12, etc., etc. So I'm just going to highlight a few of these to zoom in on. So I hope you see well on the screen. There are green boxes around 4 of these objects. This one is super well known. I'm sure you all know this. This is the Pleiades, or the Seven Sisters, a nice young star cluster. And so we can see why this one is fuzzy in this image. It's partly fuzzy because there are several stars that are close by to one another, and so they're barely resolved with the naked eye. But also there is material left over from the formation of the stars. So this sort of blue haze that you can see here. So this is mostly dust that's scattering the light around, so it makes the Pleiades look fuzzy. This is the Ring Nebula. So this is a planetary nebula. So very misleading name, because planetary nebulae, of course, have nothing to do with planets whatsoever. It's where an evolved medium mass star in the later stages of its life becomes unstable, and it throws off the outer layers. And so that's all of this brightly illuminated material that you can see here, the debris of the outer layers of the star, and then the core of the star that's left behind here in the center. This is the Crab Nebula. So it's a supernova remnant, so where a massive star has shredded itself in this cataclysmic explosion at the end of its life. So no stellar remnant left over with this one. So unlike the Ring Nebula, where you could still see the exposed core of the star left behind, this one has completely shredded. And then this last one is the Eagle Nebula. So different type of object. Once again, this is the region of stellar birth. So massive clouds of gas and dust where new stars are being formed. So you'll have noticed that several of these objects that I showed all have the word nebula in the title, and that's because when astronomers just see something that looks fuzzy and cloud-like, they call it a nebula. And so these objects, even though they're very diverse in terms of their physical origin, they're often referred to as nebulae, whether they're planetary nebulae, star-forming nebulae, or supernova remnants. But we can also see, when we look at this catalogue of Messier objects, that many of them are obviously galaxies. And at the time, they were referred to as spiral nebulae. So you can see, for example, the beautiful spiral arms in some of the galaxies in the lower rows here. And so there was a big debate back starting in sort of the late 1800s, ticking over into the early 1900s. Just saying, yes, I agree, Laurie. I agree. There was a big debate as to what was the nature of these spiral nebulae, and so any good research, in my opinion, has to start with good observations. And so some of the earliest observations of these so-called spiral nebulae in the Messier catalogue were made with this telescope, the so-called Leviathan of Parsonstown. It was located in Ireland. It's actually been reconstructed. There's a modern replica of it. So this was on the estate of Lord Ross. It was a pretty big telescope. It was 1.8 meters in diameter. The mirror was made of speculum metal, which is, if I remember, I think it's an alloy of copper and tin, I think. The big drawback being, of course, you have a metal mirror outside in Ireland. Doesn't do so well in the elements, so it would tarnish very quickly. We had to keep swapping in a spare and repolishing it. But nonetheless, Lord Ross made some of the very first observations recorded observations of these spiral nebulae and made these very famous hand drawings now. So this is a nice picture of M51, the Whirlpool galaxy. This is how Lord Rosse saw it. He could already make out that there were these nice spiral features to it. He could make out that there was a bright central nucleus, so the bulge of the main spiral galaxy. And he could also make out that there was a companion there. So that's what a modern picture of M51 looks like. So you can see he, in broad brushstrokes, he kind of captured the main features of this pair of galaxies. But the debate had to move beyond just these pretty pictures in order to figure out really what the nature of these spiral nebulae were. And this was a debate that was sort of brewing in the community and came to a head with this very famous great debate, the Shapley-Curtis debate that happened in 1920. Where Shapley on the left and Huber-Curtis on the right kind of duked it out in terms of arguing about the nature of these spiral nebulae. And so on the one hand, Shapley argued that the Milky Way was the only galaxy in the universe, and that these so-called spiral nebulae were embedded within our own Milky Way, whereas Huber-Curtis argued that these spiral nebulae were actually galaxies in their own right, but they were just small and very faint because they were a very long way away. And each of these men put forward their arguments. So, for example, Shapley argued that it was impossible to think of the great distances that would be involved if these spiral nebulae were truly galaxies. It was sort of inconceivable the scale that would require. There were also observations at the time that claim to actually see rotation in some of these spiral nebulae, which, if true, would indicate that they were rotating faster than the speed of light if they were at great distances. It turns out that these observations were actually wrong, but it was an argument put forward by Shapley at the time. So these men sort of put forward their arguments. In the end, it sort of finished as a kind of a stalemate, because fundamentally there was no evidence really to support more strongly one view over the other. And so the reason that I had constructed this talk to give at the Linecourt production of Silent Sky was because it was all about the work of Henrietta Leavitt. And I showed at the talk here, there's this great book if you're interested in knowing more about the history of the work done at the Harvard Observatory in those years, and in particular how the ladies that worked for Edward Pickering, who is this gentleman standing in the back here, who employed this large group of women, his so-called computers, to make the detailed measurements from the glass plates and to collate all of the data. And so, one of these computers, as I said, was Henrietta Leavitt, and she was the discoverer of this really important relation in a type of stars called Cepheid variables. So a Cepheid variable is one of a number of different types of star that is going to be variable for a number of different reasons. So Cepheid variables are physically pulsating, and so as they get bigger, they have a higher surface area, and so they get brighter. So that's what this little graphic on the right-hand side is showing you, how as the star gets bigger and smaller, the luminosity, so the brightness over time, gets greater and smaller. And so Leavitt's key insight was to realize that there was this tight correlation between the kind of the peak brightness of the Cepheid, so that's what's plotted on this y-axis here, and the time period between two successive peaks in this light curve. And so what she demonstrated was that the brighter the Cepheid, the longer the period. And so this kind of cartoon graph is showing you that relation. So why was this so important? Well, it was a fundamental way of figuring out the distance to these Cepheids, because you can measure the period of the light curve by observing these Cepheids over a number of nights. You can then use this relationship to look up. So let's say you measure that the period is 30 days, you then look up on the curve, you read across, and it tells you that the luminosity of that Cepheid in units of the sun's brightness is 10,000, so 10,000 times brighter than the sun. You know that's the true luminosity. You can compare that to the brightness that you measure, the apparent magnitude, and you can compare that absolute and that apparent value, and it tells you about the distance. So that was the real key finding here. And so, of course, this was used by Edwin Hubble when he measured the distances to some of the nearby galaxies and established them as being at distances far too great to be within the Milky Way. So this was really the sort of the brief history of how we came to realize that our Milky Way is just, one of many galaxies. I think it's really noteworthy that it's 100 years since these observations. I would encourage you to maybe think about some kind of anniversary celebration of this, because really, this is a really key moment. And 100 years, this is not a long time ago. And so that has been the history of galaxies just in 100 years. So Hubble then went on to define now what is called the Hubble law, which is by measuring not only the distances to these Cepheids using this period luminosity relation, but he also used spectroscopy to measure the recessional velocity, or the redshift, of these galaxies. And so he established another of these key relationships in astronomy, the so-called Hubble law, in which we see this nice tight correlation between how far away a galaxy is and how fast it's moving. This was really the discovery that triggered the idea of a Big Bang, because if things are all moving away in the past, they must have all been closer together. And so this was also the birth of the field of cosmology. And of course, the constant that defines the slope of this relation is the Hubble constant. The other thing that Hubble is really famous for, and that's going to segue us now into the second part of the talk, is his classification of galaxy morphology. So Hubble came up with this famous tuning fork classification, where on the left-hand side, this is sort of the handle of the tuning fork, he classified spheroidal galaxies, so elliptical galaxies, and he put them into classes by number, so E and then a number, and that number told you how elongated the galaxy was. And then the two tines of the tuning fork on the right-hand side, the upper branch is for spirals that don't have a prominent bar, and on the lower branch for spirals that do have a prominent bar. And then it was the tightness of the winding and the dominance of the bar that then subdivided further the A's, B's, and C's. So this was the nice, neat picture that kind of Hubble laid out for us. He had this vision that galaxies evolved from left to right. So he actually referred to ellipticals as early types and spirals as late types. We actually now know that that's not true. If anything, it's backwards. But nonetheless, he was the one who laid out this framework for galaxy morphologies. But there's always been this sort of spanner in the works, sort of problem children or black sheep of the family. And that is that there are a population of galaxies that don't fit into this nice, neat picture of the tuning fork, these so-called peculiar galaxies. And these were really studied in detail by this astronomer Chip Arp, And if you're interested in this topic, there's a really nice book. Unfortunately, I forgot to bring it tonight. It's up in my office at work. But there's this really nice book that's been put together by 2 amateur astronomers, where they have taken images of a number of these peculiar galaxies, and there's all sorts of great tips on how to observe them. So if you're interested in this, you can either order the book, but there's also a number of online resources for this as well. And you can see the full catalogue of all of these peculiar so-called ARP galaxies online. I'm happy to pass on this presentation, when I'm done, if you want to be able to copy paste some of these web links. But we're just going to have a bit of a kind of a show and tell, because I think these are just really gorgeous images to look at. So this was the one on the cover of the book. So what you're looking at here is 2 galaxies that are in the very late stages of merging together. So there's, if I get my mouse here, there's one galaxy up here, and then there's another galaxy down here. You can see all these bright regions of star formation in pink, and these dark dust lanes, and then there's all of this faint debris. So this is all from starlight, but very diffuse, and so it looks like this sort of halo around it. Here's another very well-known pair. So these 2 aren't quite as close together. So the main body of one up here and the main body of the other down here. This pair has probably had just one recent passage. And so what you're seeing is lots of material that has been stripped off into these long tails and a bridge between them as they're kind of shredding each other apart. And then this is a great one. It's where one galaxy has just, punched through the center of another galaxy and completely ripped out the middle part and just kind of left this this ring of stars behind. And trust me, you can waste endless happy hours looking at images of these. And so the Hubble Space Telescope has got a really nice compilation of many of these galaxies, which I would urge you to look at. So what's the nature of these peculiar galaxies? Well, I've already given it away. I've already told you that they're interacting galaxies, but this wasn't known from the get-go. And one of the really key pieces of research back in the 70s that allowed us to understand what was going on were these very early computer simulations that, nowadays when we run computer simulations of galaxies, we run these on supercomputers. There are billions of particles that we put in the simulations. We can simulate all of the gas physics. We put in dark matter. This is, way predates the idea of dark matter. But what was done in the 1970s was just computing with just plain old simple gravity with a few hundreds of solid particles. What happens when you throw 2 galaxies together? So what you can see in this image is the reproduction of a figure from one of these early papers where they've been trying to reproduce some of the patterns that were seen in these peculiar galaxies. And so this is actually the same image as the first one I showed you. It's just rotated and a wider field. So now you can see these long tails. And so the punchline of these early simulation papers was that they were able to reproduce the kind of shapes that were being seen in these so-called peculiar galaxies. And so, we could really start to understand that these strange shapes were being caused by gravitational interactions. So this is the movie that I had on my title slide, just to kind of contrast the kinds of simulations that we can do nowadays, not just with a few hundred particles, but with many, many millions, very high resolution. But you see all of the same features. The galaxies have this first close passage, we call this a pericenter, and then the tidal forces that the galaxies feel during that pericentric passage are what start to generate these very asymmetric structures. So these long tails and bridges that get pulled off. And then if the orbits are conducive, so if they're in a so-called bound orbit, because it's possible that these galaxies, they just whiz straight past each other. But if the orbits are favorable, they can actually capture one another, that after a few of these close passages, they actually merge together into just a single remnant. So it was the Toomray brothers that really kind of pioneered this early simulation work, and in their honor, we now define this so-called Toomray sequence. So this is a way of visually classifying the stages of the mergers. So I like to think of this as a bit like an extension to the Hubble tuning fork. The Hubble tuning fork was a way of self-organizing the different galaxy morphologies of regular galaxies, and the Toomray sequence is an attempt to try to make sense of different morphologies in interacting galaxies. And so the sequence, so you can see the numbers down in the lower left corners here, this sequence starts off with close pairs of galaxies, but these galaxies don't yet have any signs that they're doing anything interesting to each other. So they're maybe just on their first approach. They haven't started to really interact yet. And then as we move through the sequence, the disturbances become greater and greater. This is meant to be, trying to capture the time sequence until eventually you just have one single galaxy that's a complete kind of train wreck at the end. So one question I often get asked is, how come we see galaxies interacting at all, right? Space is very big. The distances between galaxies are very large, and the universe is only getting bigger, so those distances are only getting bigger. And so I like to show this graphic to explain why galaxies interact. So this is an image that maps the structure of galaxies in the nearby universe. So the way to read this is that every dot that you can see, those of you on Zoom can probably get a higher resolution picture of this with your eye than the folks in the room, but this picture is made up by putting a dot at the position of every galaxy, and when the density of those dots is higher, you see the red colors. And so the way to read this is we're in the center here, and so distance is in the radial direction. So the further away a galaxy is, the further out from the center of the circle it is. And then the right ascension is around the outside of the circle. So this is really a map, a two-dimensional rendering of the distribution of galaxies in some slice of the nearby universe. And the key takeaway point from this is that galaxies are not uniformly distributed in space. They cluster in groups and in these long filamentary structures. And then there are regions of space where there's not very much at all, these great sort of empty dark voids. And so when galaxies are in these overdense regions, in these clusters and groups, in these clusters and groups, they feel the gravity of all of their neighbors and the gravity of the cluster potential that they live in. And so they're not just moving away from everything else. They're not just moving with the Hubble expansion. They feel the gravity of all of their close neighbors, and so that they can have these close passages. So these gravitational interactions and mergers are really not rare at all. So the really extreme ones that I've shown you up until now, these are relatively rare. But when you look hard enough, you see features of mergers everywhere. So this is a very deep image of a galaxy that, if you just take a regular picture of it, just looks like a very boring elliptical galaxy. But this is a very, very deep image taken with the CFHT on Hawaii, and it reveals all of these ghostly shells. It's sort of the debris of its past interaction history, because we believe the way you build up massive galaxies like the Milky Way, like Andromeda, every massive galaxy is through a succession of mergers. And so mergers are really key to the growth and to the structure of galaxies. So this is another demonstration of how prevalent merger features are when you look. So I'm sure many of you have looked at the Andromeda galaxy. So this is the picture that you're used to seeing of it. But when you take a really, really deep image, and again, this is work that's been done but with a project that's been led here in Victoria, actually up at Hertzberg, when you take a really deep image of Andromeda, you get to see much fainter structures, and you see all of these tidal features and these shells and bridges to companions. And so again, this is the history of all of these interactions that have built up Andromeda. And then even in our Milky Way, we see it. So this is again our view of the Milky Way from within it. But what you can see over plotted here, these sort of colored streams, this is a rendering of streams that have been discovered as groups of stars. And you can see they're in these very coherent patterns. These are not globular clusters. These are not open star clusters. These are very long streams where we believe that small galaxies have fallen into the Milky Way, so a merger, and where these galaxies have been shredded and have left again these tidal streams. So this is just to highlight that mergers over the history of a given galaxy are quite common. The fraction of galaxies in the nearby universe that are currently in some kind of interaction is about 2%. So it's non-negligible. So why should we care about these interacting galaxies? Well, I've already given you one reason, which is we think this is how we build up the mass in a galaxy, both the mass in its stars, the mass in its gaps, but also the mass in its central supermassive black hole, because when two galaxies merge together, their central supermassive black holes also merge together. So this is one reason we should be interested. But another reason we should be interested is that this merger really can do catastrophic things to the galaxy. And again, I've taken this sort of historical figure from a paper from the 1970s by Beatrice Tinsley. And what they showed in this paper was that if you look at the colors of galaxies in the ARC atlas, so these peculiar, now we know, interacting galaxies, you look at their color and you compare them to colors of normal galaxies in the Hubble atlas, there's this much bigger scatter. So this axis here is a measurement of the color where blue is towards the top. So you can see that there's a much bigger scatter in their colors. But also there's an offset overall to much bluer colors. And so even in the 1970s, when folks were first starting to make physical measurements of these peculiar galaxies, they saw that they were different. They had different properties to normal galaxies. And this figure sums up our modern perspective of those changes that are happening in these interactions. I'm going to walk you through these various stages. So the way to read this schematic is to start down in the lower left and work our way around clockwise, because this is the prediction that comes from simulations and is tested with observations about how a galaxy merger transforms the galaxies that are involved in it. So you start off, you have a nice, say, spiral galaxy. It's minding its own business. It's just, evolving nice and slowly, making a few new stars a year. But if it happens to find itself in a group or in a cluster, it can have these gravitational interactions that I've described. And so this is an image of a very well-known interacting pair, where again you can see those characteristic tidal tails and bridges that I've been talking about. So this is really where the fireworks start, because simulations predict that once you start to disturb these spiral galaxies, once you start to move away from symmetric structures, you give the gas that's in the galaxy a mechanism through which it can fall to the center. So basically the galaxy forms a bar, and this bar produces a torque on the gas, and this drains angular momentum away from the gas, and the gas has to funnel to the center. That's the key point. When galaxies interact, the orbits of the stars get messed up. This pulls on the gas gets funneled to the center. So now you have all of this gas flowing towards the center. This increases the density of the gas in the middle, and this then makes a new burst of star formation, because you have more gas. Gas is the fuel for stars, so you have a big starburst in the center. And this has been simulated simulation. So that's what this panel in the middle is showing you. So this is a simulation of the rate of star formation. So this SFR, this star formation rate. So this just measures how many new stars are you forming every year in these simulated galaxies. And you can see that there's a bump here, and then there's another spike here. And this corresponds to the times in the simulation when the galaxies are having that close passage and when they're coalescing together. That's the first big thing that a merger does for you, is it generates these big bursts of new star formation. The other thing that it can do is, if that gas that gets funneled to the center can make its way all the way down onto the black hole, then that black hole now can become very active. And so as material gets funneled down, it forms a disk around the black hole. This disk gets very hot, and it can make an object like a quasar. So a very luminous, very active black hole. So the simulations predicted that these two very energetic processes, on the one hand, big bursts of star formation, and on the other hand, these actively accreting black holes, should have a catastrophic effect on galaxies. They should blow out a lot of the gas in the galaxies. And if you take out all the gas in the galaxies, you're not going to form any stars anymore. And so the galaxy should then decay down along this side of the diagram. So through this so-called post-starburst phase, you've had the big starburst, but now all of the star formation shuts down because you've got no gas left, and you end up with this so-called dead elliptical galaxy. So no more star formation, so it's red and dead. And so mergers had been predicted to be very important for this shutting down of star formation.
When does the black hole appear?
Sorry?
When does the black hole appear?
Well, how seed black holes are formed is a complete unknown. So they're formed, we know they're formed very early, because even when you look at very, very high redshift galaxies like quasars, they already have that massive black hole in place. But how they form is really an active area of research. It could be a very massive nuclear star cluster in early times, but truly it is unknown. So testing these predictions observationally has been how I have spent a good decade and a half of my life. I'm not gonna bore you with a lot of the details. I'm gonna give you a taster of one result, but I'm just going to show you this slide, which summarizes where all of my hard work goes. So on the right, you can see a compilation of some of the merging galaxies that I study. So I have catalogs of thousands of these things. They don't look as pretty as the images that I've shown you because they're further away, so they're fainter and they're fuzzier. But hopefully you can still see these things are very obviously irregular. They don't fall nicely onto the Hubble tuning fork, and they're these train wrecks that are left over when two galaxies have collided. On the left, I'm showing you some of the telescopes that I've used to study these galaxies. So I use X-ray telescopes to study the properties of the supermassive black holes in the center, because when you get accretion onto the black holes, they get very, very hot, so they show up in the X-rays. I've used radio telescopes like Arecibo, which of course is sadly no longer with us, to measure how much atomic gas there is in these galaxies, to try to find signatures of this, wholesale removal of gas. Turns out that actually post mergers still have lots and lots of gas in them, so that piece of the predictions is actually not right. I've also used a different type of antenna to look at a slightly different wavelength in the millimeter and submillimeter to measure how much molecular gas is there. And then I use optical telescopes. This is actually my main bread and butter to study the star formation. But in the last few slides, I just want to show you a very, very recent result that I just published at the end of last year, which I was very proud of because it kind of tied a knot under this sort of life cycle of predictions. So we spent the last decade or so with my graduate students proving that yes, mergers do produce big bursts of star formation. Yes, they have very active black holes. No, they don't remove all of the gas, but nobody had tested whether there was any kind of shutting down of the star formation. We thought that maybe there wouldn't be, because we found that there was still tons and tons of gas left in these mergers. So we were kind of expecting that, you know, they would still continue forming stars. But of course, being good scientists, we actually wanted to prove it quantitatively. And so this is what we did in a piece of work last year. So, okay, so what is our goal? Our goal is to test whether merging galaxies are shutting down star formation. And in the parlance of the field, we call this shutting down of star formation quenching. So when you see this word quenching, it means shutting down star formation. So we want to be able to test whether merging galaxies are more frequently quenched than regular galaxies. This is a very simple experiment. Not so simple in practice. The first thing you need is a way of figuring out whether galaxies have recently shut down their star formation. And so the way that we do this is we take the spectrum of the galaxy and we look for a particular set of features. So we look for galaxies that have this characteristic that we call post-starburst. So what does that mean? Post-starburst means there is an indication in the spectrum that this galaxy has recently had a big starburst. Okay, well, how do we do that? Well, we look to see whether the spectrum has the signature of A star. So A stars are pretty massive, and so they're fairly short-lived. So if you see the signature of an A star, so this is an A star spectrum here in blue, it's got these big, broad hydrogen absorption lines. So if you see these big, broad hydrogen absorption lines in your spectrum, you know that there's lots of these A stars there, which tells you there must have been recent star formation, okay? Because A stars only live for about 1 billion years, which I know sounds like a really long time, but it's really not. So there must have been recent star formation if you see these features. On the other hand, if you see no emission lines, so by an emission line, I mean if things like do big positive spikes on top of this spectra, if you see no emission lines, it means there's no current star formation. So the combination of having no emission lines, which is what we normally see in an elliptical galaxy because there's no ongoing star formation, but there is recent star formation, as indicated by this A star-like spectrum, then we know there was recent star formation, but there's none ongoing now. So you must have had this recent and rapid quenching. So what we do is we look in our sample of merging galaxies for these post-starburst spectra. But there was another problem we had to overcome first, and that was finding enough post-mergers, so these merged galaxies, to actually do this experiment on. And so the first step was actually to come up with this new big sample of mergers, which we did using a survey called the Canada-France Imaging Survey. It's one of Canada's biggest and deepest imaging surveys done with the CFHT. And we used all the latest and greatest technology by using AI, so machine vision. We trained a convolutional neural network to sort through all the hundreds of thousands of images, because we really didn't want to do it by eye, to find mergers. And so this was the sort of the result of the combination of this big fancy survey that Canada is just completing, and also these neural network techniques. Okay, so now we had all the ingredients we needed. We had our sample of mergers, we had spectra of them all, so we could count up how many of our mergers had this special spectral signature. But of course, we also needed a control sample because we need to know what normal galaxies are doing. So we do that. So we have a control sample of non-interacting galaxies, and we count up how many post-starburst signatures they have as well. So this is the actual figure from the paper. So it's a bit dry and boring. But essentially what this axis is telling you here is how many times more frequently did we find these quenched galaxies in mergers compared to our control sample. And we can count these post-starburst signatures in a few different ways, which is why there are 2 different colored data points. But the take-home message here is that we found somewhere between a factor of 30 and a factor of 60 more galaxies in mergers with this recently quenched star formation. So despite the fact that they've still got tons of gas left in them, they seem to be very good still at shutting down star formation. So now, of course, the $64,000 question is why, and maybe that's what I'm going to spend the next decade doing, figuring out why. Okay, thank you very much for your time, and I'm happy to take any questions. Thank you.
Wow.
Oh, wow.
Okay. So, thank you so much, Sara. Wow, the pictures, the concepts, it was amazing. And I hope you're happy to take some questions because they're starting to come in. Let's start with Jeff.
Hey, Sarah, thank you very much for the presentation. Interesting looking at your various pictures, especially of the spiral galaxies and the interacting spiral galaxies. Do you have any sense, or is there any working idea of where the initial angular momentum of the spiral galaxies came from or rose from?
Yeah, so it's because of interactions. So as galaxies move past each other in space, they exchange angular momentum this way. So it is very, very early on, where things are much more compact, and these interactions are happening much more frequently at high redshifts in the early universe. And so this is what's spinning up galaxies to start with.
Thank you.
Leslie has a question. Maybe I'll read it out because he put it in the chat. Do starbursts correlate with supernovae formation so that life on planets around stars and colliding galaxies may more likely to be extinguished? If so, do we know enough about the future Andromeda Milky Way collision to understand if life on Earth is likely to be extinguished?
So that's a multi-part question.
That's an interesting one.
So yes, when we induce higher rates of star formation, we expect the rate of supernovae to increase as well. It's actually the increase in the rates of star formation of most of these mergers is actually pretty modest. So it increases the star formation rate by a factor of 2 to 3 on average. So if you think about our Milky Way galaxy, which is a big but typical spiral galaxy, the number of new stars being formed in the Milky Way per year is like 1. The star formation rate of the Milky Way in units that professional astronomers use, it's 1 solar mass per year. So that means 1 sun-like star formed every year in the Milky Way. So it's pretty pathetic. So if a merger increases that by a factor of a few, it's not like we're going to have massive supernovae going off all over the place all the time. Now, that said, sometimes some mergers start producing stars at thousands of times that rate, but it's quite rare. The conditions, it's kind of like a Goldilocks thing. The conditions have to be just right in order for that to happen. In terms of the Milky Way and an M31, so yes, we're on a collision course with Andromeda. It's going to take a few billion years for that to fully play out. I would be delighted to think that the human race might still be going in that length of time. But the computer simulations of the Milky Way and Andromeda interaction are actually fairly modest. So again, they might increase the star formation rate by a factor of few. Stars never, well, I should say never. It's very, very, very rare for stars to actually collide in the simulations, just because the space between the stars is very massive. So would a collision, the eventual collision between the Milky Way and Andromeda, be catastrophic for life on Earth? Not in the short term. The most, I think, likely noticeable impact is that our sun is likely to get kind of flung out much further from the galactic center, but the Earth's orbit wouldn't become separated from the sun or anything like that.
And the sun's getting hotter and brighter anyway.
I was just
So
going to say,
get to us first.
we have bigger problems, I think, yeah, in terms of the.
You have time to paint your living room.
Wow. Dave Payne.
Hi, I thank you for a wonderful talk. That was great. I had read somewhere that 90% of the stars that the universe will form have already been formed. Is that true? And is it because as space gets bigger, interactions between galaxies become fewer, or are the galaxies themselves running out of gas?
All of the above. So yes, it's true. If you look at the average rate at which galaxies are forming stars, the universe is kind of in decline now. And this is something that the James Webb Space Telescope is highlighting even more for us, that large fractions of the mass in galaxies were formed very, very early on. In fact, worryingly early on. It's actually that there's really an emerging tension between the number of these very massive galaxies at very high redshift and what the models can actually kind of tolerate. But it's also so yes, it's true, most of the star formation has already happened. Why? So yes, certainly interactions were more common in the past. That's a part of it. But the bigger piece is probably just the gas in the galaxy. So if you look at the average gas content in galaxies at low redshift, it's much lower. You can replenish gas in galaxies. So galaxies don't evolve in isolation. They get continually fed with gas from the external intergalactic medium. But as the universe gets bigger, that feeding becomes less efficient. And then there's a secondary effect that very massive galaxies, as the gas is trying to flow onto very massive galaxies, that gas gets shocked. And so it gets hot and it takes a long time for it to cool, and that impedes it even further trying to flow on. So there's a number of different things.
Wow. Okay, Sara, can you, in preparation for Oliver's question, put on that animation of the collision?
Oh, yes. Sorry, I saw the comment about stopping sharing my screen, which I just did, but let me just bring back the
And then I've got a question about that also. Plus, I just like watching it.
I know. It's beautiful. Yes.
Okay, so Oliver, go for it.
Well, it was exactly what I wanted to look at. I wanted to say how beautiful this ballet is to watch. But can you give us an idea of the time scale? How many billions of years are we watching here, or millions? Or
Yeah, that's a great question. So the typical time scale you should have in mind for a simulation like this is about 1 billion years. Yeah, so it's fairly short on kind of cosmic timescales, but it's not the kind of thing that we can watch playing out in real life. So that's why things like this tumor sequence are so helpful.
And Sara, my question there is, it looks like there's friction. It looks like there's something that is, you know, when planets are going around the sun, there's no friction. And it's going to just keep doing it forever, except for a few collisions and things. Here, it looks like they don't just go around each other. They actually are, there's something inelastic.
Yeah, that's very, very perceptive. I wish my students were this observant. Because often when I say to them, you know, why do galaxies merge? Because, you know, planets don't fall into the sun, and they're like, oh, I've never thought about that before. So yes, very perceptive question. And it is friction. It's something called dynamical friction. And so this is because the galaxies have a gas halo. And so as they move through the halo of the companion, this dynamical friction effect, you can think of it as a massive particle that attracts through gravity other particles in its wake, and so that is slowing it down. It's like it's a drag, right? And so that's why the galaxies move apart, and then they appear to kind of slow down, and then have another pass. And so that friction that you're seeing is this dynamical friction, where it's the pull of the wake of stars that are formed in these gravitational interactions.
Wow.
Hmm.
It looks very much like a fluid mechanics problem.
Yeah. Yes, exactly. It is. It's exactly a fluid dynamics problem. So that's what is sort of more advanced in these simulations than those very early ones, where the very early ones just had essentially star particles. So they were particles for which you put in the laws of gravity, but now with the added hydrodynamics, so the gas physics as well, it allows you to not only get a more faithful representation, but it allows you to sort of follow these gas inflows that I was talking about that then lead to the starbursts.
So somebody named My Day, their web name, has a question. Do you want to ask it or do you want me to read it? I'll read it. So My Day says, is the quenching a temporary, whoops, I made my chat fall away. What happened to it?
Yeah, hi there, it's Michael here. Yeah, sorry, I was
Oh.
muted. Can you hear me?
Yeah.
Okay, so I was just asking you, is the quenching a temporary phenomenon or is it a permanent phenomenon? And if it's temporary, what's the duration, right? So you have this pulse of star formation, it quenches further star formation, but is that like a permanent state?
I would love to know the answer to that question. It's a really interesting question, right? Because I told you that there's still lots of gas left in these galaxies.
Yes.
So something about this gas is infertile to star formation, but is that indeed a temporary state? So for example, has it just stopped forming stars because everything is very turbulent? And so it's hard for gravity to kind of get a grip and make new stars, but given time, will that settle down and it could remake stars again? We don't know. We don't know the answer to that. You'll have to have me back in another 10 years and I'll maybe know.
And I could see how it might be challenging to do the same kind of data analysis you've just done for that situation, because you're not in that post-surge environment. So it'd be harder to come up with your sample.
So what we're trying to do now, and this is really just in the early stages, is we're trying to build off the success that we've had with working with neural networks. And we're trying to design a neural network that will be able to tell us not just this galaxy is a merger, but tell us how long ago the merger happened. Because if we can identify galaxies over a series of timescales that we can label, and we can start to see what's happening in terms of their gas contents and their star formation rates as a function of time in that kind of post-merger regime, then we can start to try to unpick that question. But the challenge is figuring out that timescale.
Thank you. So we have Brock and we have a question in the room. Go Brock.
Okay. Just when you're talking about the merger and there was talk of gas and watching the animation, it reminded me of a question I've always had about galaxies. When you're looking at a galaxy, how much of the light that you're seeing is stars that are just too darn small to see and too far away to see, and how much of it is gases within and around the galaxy that are either emitting or reflecting or doing Rayleigh scattering or something like that?
So the answer to that question really depends on the wavelength that you're looking at, right? So when we talk about mapping the gas and seeing the gas, we can really do that best when we're looking at specific wavelengths that are capturing specific processes. So for example, we can map the atomic gas at radio wavelengths because there's a particular frequency or wavelength at which we see emission from the H1. So it's at a very fixed wavelength. So it's an emission line rather than part of a continuous spectrum. So when you look at optical images of galaxies, the vast majority of that is coming from starlight. But in some small wavelength bands, there are also emission lines, but most of it is starlight.
So I imagine Brock is wondering about visual because he's one of our big astrophotographers.
But as you say, you also see the scattered light, right? So, for example, with the Pleiades, but that's very faint and very, very, very hard to see in other galaxies. So when you're talking about other galaxies, the vast majority is, it's just the straight up starting.
Okay, thanks.
Okay, in the room,
Nice and loud too for this to pick up. Yeah.
We have a lot of closer face-on galaxies, like say N33 or N101, where you can see star forming places. But when you look at elliptic galaxies, first of all, the ones I know of, like say M87 or something, is quite a bit further away. How difficult is it to sort of analyze what's in something like that with the kind of, I mean, I've got a 24-inch that I can observe through, but I can't imagine what kind of equipment you might have access to.
Yeah, so it's actually pretty straightforward to look for those kinds of star forming regions. And actually, for a long time, astronomers considered that elliptical galaxies were completely dead, like no star forming whatsoever. But it turns out when you look really, really, really hard, you can see this, they call it frosting, like this very, very light sprinkling of star formation. And likewise, it was thought that elliptical galaxies had no gas in them. Turns out when you look really, really hard, about a 25% of elliptical galaxies still have some leftover gas in them. So,
we might be slowing down only because we are so blown away by what we just saw right there. So any last questions? Well, I'm going to say, I see Miles put his hand up.
I'm just wondering if the new understandings or better somewhat understandings of dark energy and dark matter have some kind of interesting effect in all of this.
for the mergers, you mean?
Yeah, well, in the whole works, I guess, but
How do you keep track of what you can't see and measure?
Yeah, so for the merging process, the distribution of dark matter within reasonable limits doesn't actually have a big effect. Now, dark energy, of course, with making the universe expand at an ever greater rate, putting the space between galaxies ever larger, that has some impact. But as I mentioned before, these mergers are happening in these kind of self-gravitating groups and clusters that probably don't get shredded by cosmic expansion. So yeah, we still have many questions in our mind about the nature and the origin of dark matter and dark energy, but for these mergers, it's not the dominant factor.
I'm sorry. Has anyone looked at the dynamics of star forming regions after a merger? Because presumably that they have to be disrupted to do the quenching, and so the scale at which it gets back together depends on how those get back together as well.
Yes, yeah. So this is another thing that we've been doing. We've had a big program to look at, like, in a spatially distinct way, where the star formation is happening, what the dynamics are, what the gas is doing. Yes, I could keep you for a whole other hour, but I won't.
Well, you could, but we're going to take the two last questions. There's Paul in the chat and Bruce, and then we're just going to hold it on those two. So Paul, I'll read it. Do quenched galaxies have black holes?
Yes.
That's good.
all massive galaxies have black holes.
Oh, 100%. That is wonderful.
All the ones we've looked 4, we have found black holes. And when I say we, I mean the community, not me.
Okay. And Bruce, you get the last question.
When astronomers are dealing with redshifting, are they accounting for internal redshifting within galaxies, that from satellite galaxies, or from movements within the galaxy?
It depends what you mean when you say accounting for. So when we assign a redshift to a galaxy, it's, you know, it's the average velocity that we see. So, you know, one arm of the disk is slightly more blue shifted and the other arm is slightly more red shifted. And so we'll take the so-called systemic, like the central value. Is that what you're asking?
I was thinking more about when you have parts of the galaxy, such as satellite galaxies, missions, and other things that would cause different redshiftings from what the average would be.
I see what you mean. Yes. So we call these peculiar velocities, right? So you have the so-called, you know, Hubble expansion that says, if a galaxy is at this distance, this is the recessional velocity I expect it to have. But then if it's in a group or a cluster, it's got this extra component tugging on it. So that adds in to the velocity that we measure. What is very difficult to do is to separate out those components. You can only really do it in a statistical way. So if you measure all of the redshifts of galaxies in a group, you can get the systemic recessional velocity of the group. And then the little bits on top of that are the peculiar velocities. Did that, I'm not sure that 100% made sense as I'm saying it out loud. Did it answer the question?
It's about halfway answered,
Okay.
which is for peculiar redshifting what you'd expect.
Well, that definitely answers something that I was been wondering, Bruce. Okay, so again, thank you, Sara, and let's all show our appreciation.
Thank you. Thank you.
And we just have time for some announcements. I'll start. We will be sending out an announcement for the next council meeting, which will be 15 days from now, the 28th, Tuesday, the 28th, to do preparations for the AGM. But if anybody has items for the AGM, do get in touch with us. And I guess a particular pleasure is Reg is working on nominations for various awards. Is Reg on the line?
He's hiding in the room.
Oh, hi. You want to say anything about, well, I guess, first of all, positions for our new council? He's been kind of waiting to see whether we're working for next year on our old or our new bylaws, and now we're working on the new one. Thank you very much, everybody. And he is also gathering nominations for awards.
So I would say I've accosted a lot of people in this room trying to get them possibly to stand for office or maybe volunteer for one of the officer type positions that are no longer on the board but need to be signed. But if anybody has got an interest out there and I haven't contacted them and they would be interested in standing or getting more involved with the Victoria Center, please email me at pastpress@victoria.rasc.ca.
And about awards?
As well, we have a couple of awards that are standard. One is the Newton Ball Award, which is a service award, and there's information about that award on our victoria.rasc.ca website, and that is under the About area of the website, and there's a bit of information about that and past winners of that. There's also another specific award associated with telescope making and tool making, and that is called the Ernie Fanishment Telescope Award. We also have people submitting photos. I think that possibly to Joe Carr, he could speak on that, but we're assembling a large collection of photos that will be judged, and there will be awards given. And that is on our Zenfolio website.
Oh, and let me say that we will hold an online AGM, but then not long after that, we will hold a social dinner, and the awards will be handed out at that time, but in person for anybody who can come. Okay, so anything more, Reg?
No, I said too much.
You said wonderful amount. David, do you want to talk about SIGs? And oh, I think it would be really great to have a report maybe from Jill about the beginner's SIG having an in-person on Cattle Point.
Yeah, I can just a quick note. There is one SIG this week, and that's the Maker's SIG, and that's this Thursday. I think I met somebody recently that might be of interest to Michelle, who's in Quebec right now, that is thinking about building a spectroscope. So, and plus I'll probably give another report on my ongoing investigation and building a little sensor box. But maybe this is a good segue to let Jill speak to something that happened recently. Jill offered to put together some, real in-person observing sessions, and I have to say I am so pleased, Jill. You did a remarkable job last Friday when I casually when I was casually imaging the comet. A lot was going around me, and maybe you can talk a little bit about it.
Yeah, it's for the beginners, and what we're doing is working our way through the Explore the Universe RASC program. So there are, as you know, over 100 targets from constellations, stars, deep sky objects, and a bunch of planetary moon stuff. But we're starting with the constellations and the deep sky objects and the stars, and we were out looking at several of them on Friday. It was beautiful. It was quite warm, and the skies were dark, and several people came out that were not all that familiar with the constellations, and so I think they got something out of it. Tomorrow looks like it's going to be clear again, so I plan probably to head out, and I'll be sending a note to the beginners again, see if anyone else wants to come and see what they weren't able to catch the first time around.
Yeah, and actually, just as a side note, the comet was near Mars when on that Friday when Jill and I were and the rest of the SIG was out there. But tomorrow night, it's going to be next to Aldebaran. So if you want to come out, I think I certainly will try to. And if not, try to look for it from your backyard.
It's not one red dot, it's another.
Yes. Wow, I never would have thought of that, Randy.
I am so moved that, I mean, this is what we're supposed to be doing. This is absolutely amateur astronomy at its best. And I'm just delighted. And yeah, the picture, David, is beautiful. And Dan Posey's picture that he posted today, wow. So many beautiful pictures. I also want to say, take a look at various videos of the fireball that fell over the English Channel this morning. They predict it's the 7th predicted fireball ever in human history, and so lots of people had their cameras out, and it was really something. I think we might call that a day. There is no Astro Cafe next week, the 20th. It's Family Day. I wish us all clear skies and some fun with that. Again, thank you to Sara Ellison for what an amazing talk. And it's so good to see everybody. Some of you are not regulars at the Astro Cafe. do come and join. It's a lot of the life of this community is happening on Monday nights, and I think you will enjoy it here.
And we had a guest tonight from Edmonton, Alice Sterling.
Oh heavens, yes. Hi, Alistair.
Hello.
I hope you had a good time. We had a nice report from you last time, but I think considering they want to kick us out in 15 minutes, unless there's something burning, gone, have a wonderful couple of weeks. We'll see you on the 27th.
Thanks, Randy. Thanks everyone for having me.